Welcome to the Explainer. Today, we're diving into a topic that is, well, absolutely essential for anyone who works with or even near electricity. It's called NFPA 70E. Now, that might sound like just another regulation, but trust me, understanding this standard can be the difference between a totally normal day at work and a life-changing accident.
Here's the thing about electricity that makes it so tricky. It powers pretty much our entire world, but you can't see it. You can't smell it. You can't hear it. It's this incredibly powerful, ever-present force on almost every single job site, but it's so easy to forget it's even there.
And that's the problem, because when that invisible energy gets loose, the results are anything but invisible. They are devastatingly real. We're talking severe burns, electrocution, massive explosions. This, right here, is exactly why a standard like NFPA 70E even exists. Okay, so we know the stakes are incredibly high. So the first step is to really define what we're up against. What are these invisible dangers, really? Let's break down the two main hazards that we're trying to protect ourselves from. The standard really boils it down to two big threats. First, you've got the electric shock hazard. This is the one everybody thinks about, right? It's when electrical current passes through your body. That can be anything from a little zap to, tragically, full-on cardiac arrest. But then, there's the arc flash hazard. And this is a completely different beast. This is a violent, explosive blast of energy when electricity literally jumps through the air from one point to another. Think of it like a lightning bolt in a box. Blinding light, incredible heat, and a pressure wave that can throw you across a room. It is absolutely catastrophic.
So you've got the risk of shock, and you've got this insane, explosive arc flash. With dangers this severe, how on earth do you create a safe place to work? Well, that brings us to our guide, our playbook, NFPA 70E, and here it is. The NFPA 70E, the Standard for Electrical Safety in the Workplace. This is published by the National Fire Protection Association, and this document is basically the culmination of decades of experience, data, and hard-learned lessons. It is the authoritative guide for managing electrical risk. And its purpose is stated right there in the text. But I want you to focus on one word here, practical. This standard isn't about some abstract theory. It is designed from the ground up to create a genuinely safe space for employees in the real world on a real job site, day in and day out. Now, if you take away only one thing from this whole explainer, let it be this next part. The entire philosophy of NFPA 70E is built on one single overriding principle. This is the absolute cornerstone of the whole standard. The goal, first and foremost, always, is to establish what's called an electrically safe work condition. This is the default. It's the ideal state you want to be in before any work starts. And put simply, it just means the power is off, it's physically locked so no one can accidentally turn it back on, and you have personally tested it with a meter to prove there is zero voltage present. And the process to get to that safe state is called lockout/tagout, or LOTO for short. As you can see, this is way more than just flipping a switch. It's a formal, step-by-step procedure. You have to identify all the power sources, isolate the equipment, put your own lock and tag on it, and then, and this is the most important step of all, you have to test it to verify that the power is truly 100% off. Okay, so that all sounds great, right? Just turn the power off. But we all know that in the real world, shutting everything down isn't always possible. So what happens then? Let's talk about the high-risk exception to the rule, working on live equipment. And I really can't stress this enough. Working on live, energized equipment is the absolute last resort. It's the exception, never the rule. And to do it, you need a really, really good reason. Is turning it off actually more dangerous? For example, you can't just shut down the life support systems in a hospital. Or is it truly impossible because of how the equipment is designed? It's only under these super limited conditions that you can even consider it. And even if you have that justification, the work can only be done by what the standard calls a qualified person. Now listen, this is not just a job title somebody gives you. It's a specific designation for someone who has proven skills, who has deep knowledge of the equipment, and who has had the safety training to be able to identify the hazards and actually reduce the risk. All right, so let's imagine this scenario. You have the justification and you have your qualified person. What actually keeps them safe when they have to work on or near live equipment? This is where we get into the practical tools of protection. Now, this diagram, it's pulled right from the standard. And I know it looks a little complex, but the idea behind it is actually pretty simple. It shows us something called approach boundaries. Just think of them as invisible safety bubbles that surround any energized part. As you get closer, you cross into different zones, like the limited boundary and then the restricted boundary. Each zone has a higher risk, and each has its own set of rules you have to follow. And you know what? Those safety bubbles get a lot bigger as the voltage goes up. I mean, just look at this. For a 15,000-volt system, that outer bubble, the limited approach boundary, is 10 feet away. You have to be 10 feet back. But for a high-voltage transmission system, that same boundary explodes to almost 19 feet. So the key takeaway is simple. The more power in the system, the more distance you need to stay safe.
So good planning and respecting those boundaries are your first lines of defense. But when a qualified worker has no choice but to cross into that danger zone to do a job, they have to rely on their final layer of protection. This is their armor, personal protective equipment, or what we all call PPE.
Arc flash PPE is rated in a weird-sounding unit, calories per centimeter squared. All that is just a way to measure intense heat. To give you some perspective, a rating of about 1.2 is what you'd get if you held your finger over a regular lighter for 1 second. Now, look at how fast the protection levels ramp up across the 4 categories. By the time you get to Category 4, you are wearing a full multi-layer arc flash suit, a lot of people call it a bomb suit, and it's designed to withstand a massive, explosive release of energy.
Okay, so we've talked about safe work conditions, approach boundaries, PPE, but all these technical details, all these rules, they're really just pieces of something much, much bigger. Let's zoom out for a second and look at the big picture.
Because here's the most important thing to understand. Complying with NFPA 70E isn't about memorizing tables or just checking boxes on a form. It's a complete framework for building a safety culture. A culture where every single person, from the brand new apprentice all the way to the CEO, understands the risks and is empowered to work safely. And the standard is crystal clear about where that responsibility begins. It starts with the employer. They are required to establish, to document, and to implement all of these practices. A real safety culture has to be built on purpose, and it has to be maintained from the very top down. So, as we wrap up, I want you to think about this question. And it's not just a rhetorical one. Whether you're the one on the tools or you're in the office, think about your own workplace. Is there a panel that isn't labeled? Is somebody's training out of date? Is there a lockout procedure that people sometimes ignore? What is the one step you can take tomorrow to improve electrical safety where you work?